In the quiet years following the First World War, the world of science was standing at a crossroads. The old certainties that had guided humanity for centuries were beginning to tremble. For generations, physicists had believed in a universe that behaved like an exquisite clock, every gear, every motion predictable, measurable, and bound by the strict laws of Newton. But as scientists began to probe deeper into the atom, that comforting order started to unravel. The atom, once thought to be a solid and indivisible particle, revealed itself to be a ghostly swirl of energy and probability. It was in this strange twilight between the seen and the unseen that a young German physicist named Werner Heisenberg emerged, a mind destined to shake the very foundations of knowledge. Heisenberg was not just a man of numbers and symbols, he was a thinker who dared to question the soul of science itself. Born in 1901 in Würzburg, Germany, he grew up at a time when the scientific world was basking in triumph. The equations of Newton and Maxwell had united mechanics and electromagnetism into a grand, coherent picture of the cosmos. Everything, it seemed, could be calculated if one simply knew enough. But Heisenberg sensed something different beneath that perfect order. He felt a tension, a whisper that the universe might not be so easily tamed. As a student under the great Niels Bohr, Heisenberg entered the mysterious realm of atomic physics, a field that had already begun to fracture the old certainties. Electrons refused to behave like tiny planets orbiting a nucleus, as classical mechanics predicted. Instead, they leapt between energy levels without traversing the space in between, as if defying the very concept of motion. This was a world where the familiar rules of cause and effect seemed to crumble, replaced by something more elusive. Bohr had proposed that these strange leaps could only be described statistically in terms of probabilities rather than certainties. For the young Heisenberg, this idea was both thrilling and unsettling. How could the building blocks of reality behave in such unpredictable ways? The year was 1925, and Heisenberg found himself on the island of Helgoland in the North Sea, battling not only hay fever but also a philosophical storm raging within his mind. It was there, amid the isolation and salt air, that he began to strip physics of everything that could not be directly observed. He asked a bold question. What if we only describe what can be measured, what can be seen in experiments, and abandon all the invisible assumptions about how particles really move? It was a radical shift. In that moment, Heisenberg was tearing down centuries of scientific tradition. For Newton, knowledge was the ability to predict with absolute precision. For Heisenberg, it was the courage to accept that nature might not give us that precision at all. His approach gave birth to what became known as matrix mechanics, a mathematical framework so abstract that even his peers struggled to comprehend it at first. But beneath the strange symbols lay a new way of seeing the universe. Instead of describing the path of an electron as a definite trajectory, Heisenberg described its behavior as a set of possible outcomes, each one governed by probability. The certainty of classical physics dissolved into a shimmering haze of possibilities. The electron was no longer a small ball following a predictable path, but a blur of potential existence, defined only by the act of measurement. This was the dawn of quantum uncertainty. The rise of quantum uncertainty was not just a scientific discovery, it was a revolution in human thought. For centuries, philosophers and physicists had believed that if we could measure everything with enough precision, the future would unfold with perfect predictability. Heisenberg shattered that illusion. He discovered that the very act of observing nature disturbs it. When we try to pinpoint the position of a particle, we inevitably blur its momentum. When we measure its momentum, its position becomes uncertain. There is a fundamental limit to what can be known, an intrinsic fuzziness built into the fabric of reality itself. This realization was both beautiful and terrifying. It meant that nature was not the mechanical clockwork imagined by Newton, but a living, breathing dance of probabilities. In Heisenberg's universe, chance was not the enemy of science but one of its deepest truths. The cosmos was no longer a perfectly wound machine, It was an orchestra playing a symphony of uncertainty. Each note, each vibration, was guided not by certainty but by possibility. Yet, as revolutionary as it was, this idea did not emerge in isolation. Heisenberg was part of a generation of physicists who were reimagining reality itself. Across Europe, brilliant minds like Schrödinger, Dirac, and Born were uncovering the strange laws governing the subatomic world. But Heisenberg's contribution stood apart because it struck at the heart of human perception. He wasn't just redefining how particles behaved, he was redefining what it meant to know something. His work suggested that there were limits to human knowledge, not because of technological shortcomings, but because the universe itself was built with boundaries of knowability. In the candle-lit halls of Copenhagen's Institute for Theoretical Physics, debates between Heisenberg and his mentor Bohr echoed late into the night. Could uncertainty truly be fundamental, or was it merely a reflection of our ignorance? Bohr believed that reality did not exist in a definite state until observed. Heisenberg's equations seemed to confirm that belief. Together, they forged what became known as the Copenhagen interpretation of quantum mechanics, a vision of a world where observation and reality were intertwined in ways the human mind could barely grasp. It was an era of intellectual daring unlike any other. To many, quantum uncertainty seemed absurd, even blasphemous. How could the universe operate without absolute laws? How could scientists build knowledge on probabilities instead of certainties? Yet, experiment after experiment confirmed Heisenberg's principle. Nature refused to obey the old rules. Every time physicists tried to measure subatomic particles with greater precision, uncertainty emerged like a shadow that could never be erased. It was as if the universe was whispering, "You may see me, but never completely." The philosophical consequences were enormous. Heisenberg's discovery did not just change physics, it changed the way humanity understood reality. It blurred the line between the observer and the observed, suggesting that consciousness itself played a role in shaping what we perceive. The idea that measurement affects reality hinted at a deeper connection between mind and matter, one that philosophers and scientists still debate today. What Heisenberg had uncovered was not merely a law of physics, but a mirror reflecting humanity's eternal struggle with knowledge and mystery. Imagine, for a moment, the magnitude of this realization. For thousands of years, humanity had sought certainty, a stable foundation upon which to build its understanding of the cosmos. From Aristotle to Newton, the goal was always to uncover unchanging truths. But Heisenberg showed that the universe might not offer such comfort. Beneath the surface of every atom lies a realm where certainty dissolves, where the future cannot be predicted with infinite precision, no matter how powerful our instruments become. Reality at its core is woven from the threads of uncertainty. For Heisenberg, this was not a defeat but a revelation. In embracing uncertainty, he believed science could become more honest, more reflective of the true nature of the universe. He often said that the more precisely we try to measure one aspect of a particle, the less we can know about another. This was not a flaw in human perception, it was a law of nature itself. The uncertainty principle was not about ignorance, it was about truth. It revealed that the universe operates on a delicate balance of possibilities, a balance that gives rise to the complexity and beauty we observe. The rise of quantum uncertainty also marked a profound cultural shift. It echoed through philosophy, art, and even literature. Thinkers began to question whether reality itself was objective or shaped by perception. Artists found inspiration in the idea of multiple perspectives, uncertain boundaries, and fragmented forms. In many ways, Heisenberg's science mirrored the changing spirit of the 20th century. A world grappling with chaos, ambiguity, and the collapse of old certainties. Just as nations were rebuilding from war, physics too was rebuilding its understanding of reality from the ruins of classical thought. Heisenberg's journey was not without turmoil. His revolutionary ideas were met with skepticism and even hostility from some of the greatest minds of his time. Einstein, the towering figure of theoretical physics, could not accept a universe ruled by chance. God does not play dice, he famously declared. To Einstein, uncertainty was an imperfection, a sign that quantum theory was incomplete. But Heisenberg saw things differently. He believed that chance was not chaos, but the natural language of the cosmos. He once remarked that the universe is not a book written in deterministic lines, but a poem written in probabilities. This poetic vision of science was both daring and profound. It invited humanity to see the universe not as a machine but as a mystery, something to be explored, not conquered. Heisenberg's rise to prominence symbolized the dawn of a new kind of thinking, one that embraced paradox rather than fleeing from it. His uncertainty principle was not just a formula, it was a philosophy. It taught scientists that to truly understand the universe, they must first accept its ambiguity. Even the mathematical beauty of his equations carried a quiet elegance. Within the cold symbols of matrix mechanics lay an idea that resonated with almost spiritual depth, that knowledge and uncertainty coexist, that the closer we come to understanding, the more we realize how much remains hidden. In Heisenberg's world, uncertainty was not the enemy of knowledge but its very foundation. It was the dynamic tension that made discovery possible. As his ideas spread, they ignited a transformation that extended far beyond the laboratory. Quantum mechanics became the bedrock of modern physics, leading to technologies that would shape the 20th and 21st centuries. From transistors and lasers to quantum computing and cryptography, every leap forward owes something to the uncertainty Heisenberg revealed. Yet, even amid this progress, the philosophical question remained: what does it mean to live in a universe where uncertainty is fundamental? For Heisenberg, that question never lost its wonder. He often reflected that science was not about eliminating mystery, but deepening our relationship with it. Each discovery, he believed, brought us closer not to certainty, but to awe, to a more intimate understanding of nature's complexity. His rise, from a curious student to one of the architects of quantum theory, was a journey through that awe, a journey into the heart of uncertainty itself. And so, as the tides of history carried humanity into the modern age, Heisenberg's revolutionary thinking became a compass pointing toward a new kind of truth, a truth that was dynamic, relational, and alive. The rise of quantum uncertainty was not merely a chapter in the story of physics. It was the awakening of a new human perspective, one that saw knowledge not as a final destination, but as an ever-unfolding voyage through the mysterious fabric of existence. As the sun of the 1920s set behind Europe's fragile peace, Heisenberg's new vision of physics began to ripple outward, unsettling and inspiring in equal measure. Universities buzzed with whispers of a young theorist who had overturned the pillars of classical certainty. Professors who had spent lifetimes studying the predictable mechanics of the cosmos now faced an unsettling truth. The universe they thought they understood was no longer the same. Beneath its orderly facade lay a restless, vibrating chaos, a realm of probability and shadow where even the concept of reality had to be reconsidered. Heisenberg himself was aware of the magnitude of what he had unleashed. He once wrote that his equations felt as though the ground beneath my feet were dissolving. For centuries, science had stood on the firm foundation of determinism. Given the position and velocity of every particle, the future could be predicted with perfect precision. But in Heisenberg's world, that foundation had cracked. The act of measurement itself introduced uncertainty. Observation was no longer passive but participatory. The observer and the observed were bound together in a cosmic dance that neither could escape. This radical shift forced scientists to reimagine what it meant to know. The universe could no longer be described as a system of solid objects following absolute paths. Instead, it became a tapestry woven from waves of probability. Every particle was a possibility field, a cloud of potential outcomes that only became concrete when measured. The more precisely one tried to grasp its position, the more its motion slipped into obscurity. The universe seemed to guard its secrets through a veil of uncertainty, as if reminding humanity that knowledge has boundaries. It was an intellectual earthquake, and its tremors reached every corner of physics. Experiments confirmed what Heisenberg's mathematics predicted: electrons defied classical trajectories. Light behaved as both wave and particle. Energy came in discrete quanta rather than a continuous flow. The deeper scientists looked, the more the universe resembled a mirage, real yet elusive, tangible yet shifting. Heisenberg's uncertainty principle was not a limitation of instruments or human error. It was the fingerprint of nature itself. Imagine the scene in those early years of discovery. In smoke-filled lecture halls and dimly lit laboratories, young physicists debated late into the night, chalk dust drifting through the air like cosmic dust. Bohr would pace back and forth, arguing that quantum mechanics described not an objective reality, but our interaction with it. Einstein would raise his brows and counter with his famous objection to chance. Heisenberg, caught between admiration and conviction, defended the strange new world he had revealed. These were not mere academic quarrels. They were struggles over the very definition of truth. Outside the realm of theory, the implications of uncertainty began to echo through culture and philosophy. The neat, mechanical worldview of the 19th century gave way to a more fragmented, introspective era. Artists embraced abstraction, writers explored ambiguity, and philosophers pondered the limits of human perception. It was as though Heisenberg's principle had escaped the laboratory, seeping into the consciousness of an age disillusioned by war and searching for meaning in a shifting world. The universe no longer promised order, it whispered of complexity, chaos, and the beauty hidden within uncertainty. For Heisenberg, the philosophical weight of his discovery was immense. He saw in it not despair but wonder. He believed that uncertainty was the essence of life itself, a sign that reality was not static but creative, always unfolding. He spoke of the universe as a great symphony, each particle an instrument whose notes could never be entirely predicted. What we observe is not nature itself, he once said, but nature exposed to our method of questioning. In that single sentence lay a profound humility. Science was not about conquering nature, but conversing with it. The rise of quantum uncertainty also brought an ethical and spiritual dimension to Heisenberg's thought. Raised in a Germany steeped in philosophy and music, he often compared physics to art. Just as a musician cannot capture every nuance of a symphony in notation, a physicist cannot capture every truth of the universe in equations. What mattered was not absolute precision but harmony, an understanding of how the parts relate within the whole. To know that one cannot know everything, he believed, was the beginning of wisdom. As the 1930s approached, Heisenberg's ideas had become the cornerstone of the new quantum theory. Schrödinger's wave mechanics and Heisenberg's matrix mechanics were found to be two sides of the same coin. Together they formed the strange, elegant architecture of quantum mechanics, the most successful yet philosophically puzzling theory in all of science. Technology soon caught up. Quantum principles explained the behavior of semiconductors, the glow of neon lights, and the fusion that powers the stars. Yet, for all its practical triumphs, the theory carried a haunting mystery. What, after all, was real, if everything existed only as probability until observed? Heisenberg grappled with that question throughout his life. During the dark years of the Second World War, he found himself entangled in the politics of a nation descending into madness. He led Germany's nuclear research, but his heart remained in the realm of philosophy. After the war, reflecting on both science and human tragedy, he wrote that the uncertainty principle mirrored the moral uncertainty of his time, the realization that knowledge and power, once thought to guarantee progress, could also lead to destruction. Uncertainty, he suggested, was not only a property of particles but a condition of the human soul. In the decades that followed, quantum uncertainty continued to expand its influence. The discovery of quantum tunneling, the birth of quantum computing, and the mysterious entanglement of particles all traced their lineage to Heisenberg's vision. Each new breakthrough seemed to reaffirm his insight: The universe is relational, interconnected, and forever beyond total comprehension. Even in the vastness of the cosmos, the faint whisper of the uncertainty principle can be heard, shaping the formation of stars, the behavior of black holes, and the dance of subatomic particles. Yet what makes Heisenberg's rise truly extraordinary is not only the science, but the courage behind it. To challenge the deepest assumptions of one's field requires a rare blend of intellect and imagination. Heisenberg's willingness to embrace paradox turned him into a symbol of scientific humility, a reminder that true understanding often begins with doubt. He did not destroy certainty for the sake of chaos. He revealed that uncertainty itself is the source of creativity. It is the space where discovery happens, where possibility takes form. Picture a universe born from that principle, every atom a story unfinished, every event a choice among countless alternatives. The uncertainty principle suggests that the universe is not a script already written, but a performance forever unfolding. Each observation, each interaction, helps shape what will be. In that sense, Heisenberg's insight was not merely about physics. It was about existence itself. Reality is participatory, dynamic, alive. As quantum theory matured, new generations of scientists built upon his foundation, exploring questions that bordered on the philosophical. Could parallel worlds arise from quantum possibilities? Could consciousness itself influence reality? While such ideas remain speculative, they all trace back to Heisenberg's radical step, accepting that knowledge has limits and that those limits are woven into the universe's design. Without that step, modern physics would still be trapped in the cage of determinism, blind to the shimmering complexity of the quantum world. Heisenberg lived to see his principle become one of the most tested and confirmed ideas in science. Yet he remained a philosopher at heart. In his later years, he often spoke of the unity of nature, the harmony between science and spirit. He believed that quantum uncertainty was not a sign of disorder but of deeper order, an order so subtle that it could only be glimpsed through its shadows. The more precisely the position is determined, he wrote, the less precisely the momentum is known. To him, this was not just an equation, it was a metaphor for life. The more we try to fix the world in rigid certainty, the more we lose sight of its motion, its vitality, its mystery. From that perspective, the rise of quantum uncertainty was not the end of predictability, but the birth of a new way of seeing. It taught humanity that ignorance is not failure but frontier, that the unknown is not a void but a wellspring of possibility. It invited scientists, artists, and thinkers alike to embrace ambiguity as the heart of creativity. In a universe governed by uncertainty, every moment holds infinite potential. Every discovery opens more questions than it answers. This, perhaps, was Heisenberg's greatest gift, a vision of knowledge that remains humble before the infinite. Today, nearly a century after his breakthrough on that windswept island of Helgoland, Heisenberg's question still resonates. Can we ever truly know the universe? The answer, whispered by every particle and echoed by every star, is both yes and no. We can know patterns, relationships, probabilities, but never total certainty. And in that delicate balance between knowing and not knowing lies the beauty of existence. The uncertainty principle, once a mathematical curiosity, has become a philosophical compass, guiding our understanding of everything from subatomic particles to the fabric of space-time. As the documentary of history continues to unfold, Heisenberg stands as one of its most profound narrators. His life reminds us that science is not merely a collection of facts but a journey of imagination, humility, and awe. He questioned everything we knew about the universe, and in doing so, he illuminated the vastness of what we do not know. The rise of quantum uncertainty was, in truth, the rise of a new human consciousness, one that sees the universe not as a static object to be measured, but as a living mystery to be experienced. And so, when we look up at the night sky, shimmering with distant galaxies, or when we peer into the microscopic world of particles, we are seeing through Heisenberg's eyes. Every flicker of starlight, every atom of our being, dances to the rhythm of uncertainty. It is a reminder that the universe is not fixed but forever becoming, that knowledge itself is a dialogue between mystery and understanding. Heisenberg's legacy endures not because he solved the riddle of existence, but because he revealed that the riddle is endless, and that within that endlessness lies our greatest wonder. The rise of quantum uncertainty, then, is not merely a chapter in the history of science, it is a story of transformation, of a world that learned to embrace the unknown, and of a man who found in uncertainty not confusion, but truth. From that truth, all modern physics was born. From that uncertainty, the universe continues to unfold. For more than 2 centuries, the universe was a kingdom ruled by certainty. Since Isaac Newton's time, the cosmos had been viewed as a perfect clockwork, its gears made of stars, its laws written in elegant mathematics. Everything from the motion of the moon to the flight of an arrow could be predicted with flawless accuracy. To know the forces and positions of all particles, Newton believed, was to know the entire future of the universe. This belief became the backbone of classical physics, a world where reason triumphed over chaos and where nature obeyed laws as rigid as steel. But by the dawn of the 20th century, cracks began to appear in that magnificent machine, and through those cracks crept something far more mysterious. It was the beginning of the end for Newtonian certainty. The story of how this certainty began to crumble is one of both genius and disobedience, a story of scientists who dared to question everything that had once seemed unshakable. In the 19th century, physics appeared complete. Maxwell's equations had united electricity and magnetism into a grand theory of electromagnetism. Thermodynamics had explained heat, energy, and entropy. Newton's mechanics still reigned supreme in describing motion and gravity. It was a time of confidence, so immense that some scientists even declared that physics was essentially finished, that only a few small clouds remained on the horizon. Yet those small clouds would soon unleash the storm that would tear down the classical order. One of those clouds was the mystery of light. Was it a wave or a particle? Experiments had proven both, yet classical theory could not reconcile them. When physicists observed how light behaved in the photoelectric effect, when shining light on metal caused electrons to leap out, they found that only light of certain frequencies worked. No matter how intense the light, it was as if energy came in discrete packets, not a continuous flow. This simple observation violated the smooth, predictable laws of Newtonian physics. Max Planck, a quiet, methodical German physicist, stepped forward with a daring idea: energy is quantized. It comes in tiny, indivisible packets called quanta. That single thought cracked the foundation of classical determinism. Still, Planck treated his discovery as a mathematical trick, not a revolution. But soon after, Albert Einstein took the idea further. He proposed that light itself was made of quanta, particles later called photons. It was a breathtaking claim, suggesting that nature was not the seamless continuum Newton imagined, but a granulated fabric of energy and probability. Einstein's theory of relativity deepened the fracture even more. Time and space, which had stood as absolute pillars in Newton's world, were now relative, stretching and bending under the influence of motion and gravity. The cosmos, once thought to be a fixed stage, became a dynamic performer. Yet the true challenge to classical physics came not from the vastness of the universe, but from its tiniest constituents. As scientists peered into the atom, the old laws faltered. Electrons refused to behave like miniature planets orbiting a sun-like nucleus. Their orbits could not be predicted with precision. Their energies seemed to leap discontinuously from one state to another. No matter how much one calculated, the equations of classical mechanics failed to explain these bizarre behaviors. It was as though the microscopic world spoke a different language, one that ignored the logic of Newton's cosmos. Into this confusion stepped a generation of young physicists who were unafraid to question everything. Among them was Werner Heisenberg, a sharp-minded thinker who had grown up admiring the clarity and harmony of classical thought but felt confined by its limits. He, like others of his time, realized that the old vision of physics could no longer hold the weight of new discoveries. The universe was no longer a flawless mechanism ticking in eternal precision. It was alive with unpredictability, fluctuation, and chance. The challenge to classical physics had begun, and it was unstoppable. The fall of Newtonian certainty was not sudden. It was a slow unraveling. First, relativity had dethroned absolute space and time. Then quantum theory dismantled the notion of absolute predictability. Together, they rewrote humanity's relationship with reality. In Newton's universe, if one knew the position and velocity of every particle, the future could be foretold indefinitely. In Heisenberg's universe, that dream was impossible. The uncertainty principle declared that there was a fundamental limit to knowledge. One could not know both a particle's position and momentum simultaneously. The very act of measurement disturbed the system, making perfect prediction a myth. This realization was like a thunderclap in the temple of science. For centuries, determinism had been a kind of faith, a belief that nature was governed by immutable laws and that human intellect could uncover them all. But Heisenberg's discovery shattered that faith. It revealed that nature was not a passive object waiting to be measured, but a participant in the act of observation. The observer and the observed were no longer separate. In that revelation, the world of Newton gave way to something far stranger and more profound. A universe governed by probabilities, not certainties. The philosophical implications were staggering. Newtonian physics had offered comfort in its orderliness. Every effect had a cause, every motion a reason, every phenomenon a place in the cosmic machine. But the new physics introduced ambiguity and paradox. It spoke of particles that were also waves, of light that behaved like both matter and energy, of realities that existed only when observed. The human mind, long accustomed to solid ground, found itself adrift in a sea of uncertainty. The universe had not changed, only our understanding of it had. And in that transformation, humanity discovered that the truth was far more mysterious than it had ever imagined. Heisenberg's challenge to classical thought went beyond equations. It struck at the heart of human philosophy. Newton's world had been one of separation. Subject and object, observer and observed, mind and matter. Heisenberg's world erased those boundaries. Reality was no longer something out there, fixed and waiting to be discovered. It was something that unfolded in relation to the observer. This was not merely science, it was a redefinition of existence itself. The fall of Newtonian certainty was, in essence, a fall from the illusion of control, a realization that even the universe has mysteries it refuses to surrender. In lecture halls across Europe, young physicists absorbed these revelations with awe and confusion. The equations of classical mechanics, once the unshakable pillars of truth, now seemed like shadows of a deeper, more elusive reality. Bohr, Schrödinger, and Heisenberg debated what this new reality meant. Could one still speak of an objective world, or was everything filtered through the act of observation? Schrödinger's famous cat, both alive and dead until observed, became a symbol of this paradoxical universe. The simplicity of Newton's clockwork gave way to the complexity of quantum possibility. Outside academia, the implications of this intellectual upheaval resonated with the spirit of the age. The early 20th century was a time of disillusionment and change. The Great War had shattered empires and faith in human reason. Artists abandoned realism, philosophers questioned meaning, and politics grew unstable. In a sense, physics was mirroring the world's psychological transformation. The certainty of the old order was gone, replaced by anxiety, ambiguity, and the search for new foundations. Heisenberg's uncertainty became not just a scientific principle, but a metaphor for the age itself, a reflection of a civilization learning to live without absolute truths. For those who grew up under Newton's shadow, this was both liberation and loss. The universe was no longer a rigid machine, but a fluid mystery. Determinism had promised control, the ability to predict, manipulate, and dominate nature. Quantum theory replaced that promise with humility. It told humanity that nature would always retain some of her secrets, That knowledge would always come with boundaries, and in that humility lay wisdom, for uncertainty was not chaos, it was the pulse of life itself. Without it, there could be no spontaneity, no creativity, no freedom. In Heisenberg's mind, this realization was not destructive but beautiful. He saw the fall of classical certainty as the dawn of a new kind of understanding. Science, he believed, must evolve beyond the illusion of omniscience. It must embrace mystery, acknowledge limits, and seek harmony rather than dominance. The universe, after all, was not a machine to be taken apart, but a living system to be understood in relationship. This philosophy marked the true end of Newtonian physics, not as a failure, but as a transformation. Classical physics was not wrong, it was simply incomplete, a magnificent approximation of a deeper, more intricate truth. By the late 1920s, this new quantum worldview had taken root. Experiments confirmed again and again that the universe behaved according to probabilities, not certainties. The motion of electrons, the decay of atoms, the behavior of light, all followed patterns that defied classical predictability. Newton's equations still worked beautifully for planets and projectiles, but they crumbled in the quantum realm. The fall of Newtonian certainty was complete. Humanity had entered a new era of science, one defined not by perfect knowledge, but by the delicate balance between what can be known and what must remain unknown. Yet even in this uncertainty, there was power. Out of the collapse of classical physics emerged the foundations of modern technology. The transistor, the laser, the computer, and the quantum devices that now shape the world all owe their existence to the theories that replaced Newtonian mechanics. The death of determinism gave birth to innovation. In that sense, Heisenberg's challenge was not destruction. It was creation. By questioning everything, he and his contemporaries built a deeper, more dynamic vision of the cosmos. As Heisenberg once reflected, the problems of physics are not only problems of physics, they are problems of philosophy. His challenge to classical thought was more than a scientific revolution, it was a reawakening of human consciousness. It forced the world to confront the limits of reason and the necessity of wonder. The fall of Newtonian certainty did not mean the end of truth, it meant the beginning of a truth more subtle, more profound, and infinitely more alive. As the curtain of the 20th century lifted, the stage of science found itself lit by an uneasy glow. A world both illuminated and haunted by the cracks that had begun to spread through the marble of Newtonian thought. Heisenberg, standing amid that growing dissonance, was no longer just a young physicist searching for equations, he had become a witness to the unraveling of centuries of confidence. The great cathedral of classical physics, erected by minds like Galileo, Newton, and Maxwell, was trembling at its foundations, and Heisenberg's uncertainty principle was one of the tremors reshaping its structure forever. For generations, science had been a symbol of stability. Newton's laws had given humankind a sense of order in the cosmos, turning motion into mathematics and chaos into predictability. The planets moved with clockwork precision, the fall of an apple could be explained with the same laws that guided the stars. But in the early 1900s, as scientists probed deeper into the nature of light matter and energy, those same laws began to falter. Electrons didn't move in neat, circular orbits, light refused to behave like a simple wave, and energy itself seemed to leap and shimmer in discontinuous bursts. Quanta. Heisenberg entered this scene not as a destroyer, but as a seeker. Someone who felt that the world beneath the atom was whispering a truth that mathematics had not yet captured. He was part of a new generation that sensed that reality was more fragile, more mysterious than Newton's clockwork universe had ever allowed. What made Heisenberg's approach revolutionary was not just his mathematics but his philosophy. The belief that the observer could never be separated from what was being observed. In classical physics, the scientist stood apart from nature, watching and measuring it without consequence. But Heisenberg shattered that illusion. To observe an electron was to disturb it, to alter its motion simply by trying to know it. The universe, once passive and predictable, became interactive and uncertain. As this idea took root, it sparked both fascination and fury. Many physicists felt betrayed, as though the universe had broken an unspoken promise. Newton's mechanics had offered a world of absolutes: force, mass, acceleration, all tied together by precise, universal laws. Now, Heisenberg was saying that those absolutes dissolved at the quantum level. The closer one looked, the less certain one became. The act of measurement, once a symbol of control, was now a symbol of limitation. Einstein could not accept this fall from determinism. His deep intuition told him that the universe must be ordered, that beneath the apparent chaos lay hidden variables waiting to be uncovered. To him, Heisenberg's uncertainty principle was not a revelation, but an admission of defeat. A sign that physics had reached the boundaries of its understanding. Yet Heisenberg saw things differently. He believed that uncertainty was not the enemy of knowledge, but its evolution. It was a new kind of truth, one that reflected the living pulse of the universe rather than the cold geometry of equations. The debate between Heisenberg and Einstein would become one of the most profound dialogues in the history of science. It wasn't merely a clash of intellects, it was a clash of worldviews. On one side stood Einstein's cosmos, elegant, deterministic, ruled by hidden precision. On the other stood Heisenberg's quantum world, dynamic, elusive, built on probabilities and paradox. It was as if two realities had collided, one mechanical, the other alive with possibility. In this intellectual storm, Heisenberg's ideas gained strength not through certainty but through survival. Each experiment that confirmed the strange behavior of particles, wave interference, energy quantization, the duality of light, added weight to his principle. Classical physics could no longer explain why electrons seemed to vanish into probability clouds, why atoms emitted light at discrete frequencies, or why even the smallest measurements defied absolute precision. The fall of Newtonian certainty was not an act of rebellion, it was a surrender to truth. As Heisenberg refined his matrix mechanics, a mathematical framework that replaced clear trajectories with arrays of possibilities, the scientific world began to see that the universe itself was not built on solid ground, but on a foundation of probabilities. The language of physics was changing. Words like position and momentum no longer described concrete realities, but shifting tendencies, like ripples in a cosmic sea. The determinism that had guided scientists for centuries was giving way to a new principle, one that accepted ambiguity as part of the structure of nature itself. This transformation was not easy to accept. It required scientists to think not as engineers of a fixed world, but as explorers of a dynamic one. It challenged the deepest assumptions of human thought, that if something existed, it must be measurable, and if measurable, predictable. Heisenberg showed that reality was not so obedient. The universe, he proposed, had layers of meaning beyond human reach, not because we lacked the tools to see them, but because the nature of existence itself was built on uncertainty. In laboratories across Europe, the echoes of Heisenberg's theory began to resonate. Physicists like Dirac, Pauli, and Schrödinger expanded on these strange new ideas, weaving them into the tapestry of quantum mechanics. Classical physics was not entirely destroyed. Its laws still worked for the macroscopic world, but its dominance was broken. A new duality emerged, a world of predictability for the large and a world of uncertainty for the small. Between these two realms stood Heisenberg's principle, a bridge between order and chaos. Outside the realm of equations, this fall of certainty rippled through philosophy, art, and even culture. The early 20th century was already a time of upheaval, world wars, political revolutions, and a growing sense that the old ways of understanding life were collapsing. Heisenberg's ideas resonated with this spirit of uncertainty. Just as nations questioned authority and societies reevaluated morality, science too was confronting its limitations. The fall of Newtonian determinism mirrored the fall of cultural stability. The world was no longer a clock, it was a symphony of chance. As the years passed, Heisenberg became both a symbol of brilliance and a source of discomfort. His principle had torn open a wound in the human desire for absolute knowledge. Yet within that wound lay something beautiful, a deeper connection to nature's truth. By showing that even the smallest particle defied full understanding, Heisenberg reminded humanity of its place in the cosmos, not as masters of the universe, but as participants in its unfolding mystery. The fall of Newtonian certainty was not the end of order. It was the beginning of humility. It taught scientists that knowledge has boundaries, and within those boundaries lies wonder. Heisenberg's uncertainty principle was not a rejection of science but its evolution, a step into a more profound relationship with the universe. It transformed how we think, how we measure, and even how we dream about reality itself. In the decades that followed, quantum mechanics would not only survive but thrive, becoming the foundation for technologies unimaginable in Newton's world: lasers, semiconductors, quantum computers. These inventions were living proof that uncertainty was not chaos, but creation in disguise. The fall of classical physics was not a collapse, but a metamorphosis, the old world shedding its rigid skin to reveal a universe alive with probabilities. And as the 20th century closed, Heisenberg's name remained etched not just in the annals of science, but in the fabric of thought itself. His challenge to classical physics had not merely rewritten textbooks, it had redefined reality. The Newtonian dream of total knowledge had faded, replaced by something far more profound: the understanding that mystery is not ignorance, but the soul of discovery. In the quiet after the revolution, as physicists turned their eyes to the stars and the quantum void alike, Heisenberg's lesson endured. The universe is not a puzzle to be solved, but a story to be experienced. A dance of light and probability, where certainty gives way to wonder, and every measurement is a dialogue between mind and matter. Through the fall of Newtonian certainty, Heisenberg gave humanity something greater than control. He gave us awe. In the dim glow of a summer evening in 1927, a young German physicist sat on the rocky shores of Helgoland, a remote island in the North Sea. The waves crashed against the cliffs with an ancient rhythm, and the wind carried the sound of distant storms. Werner Heisenberg, exhausted and ill, stared into the vast horizon, a man on the edge not only of discovery but of comprehension itself. His mind had been wrestling with an impossible problem, one that threatened to tear the very logic of science apart. He had spent sleepless nights haunted by equations that refused to make sense, and yet, somewhere between the roar of the sea and the whisper of intuition, a new truth began to take shape. That night, the universe revealed its most elusive secret, the principle of uncertainty. Heisenberg had not set out to destroy the foundations of physics, he had set out to save them. Classical mechanics, the proud creation of Newton, had been crumbling under the weight of atomic paradoxes. Light behaved as both a wave and a particle. Electrons seemed to vanish into thin air and reappear elsewhere. Experiments yielded patterns that defied reason. The deeper physicists looked into the subatomic world, the more it slipped through their fingers. Heisenberg believed that the problem lay not in nature itself, but in the way humans tried to describe it. Perhaps, he thought, it wasn't nature that was uncertain, it was knowledge. In that moment of insight, the uncertainty principle was born, not from a calculation, but from a revelation. Heisenberg realized that it was impossible to know both the position and the momentum of a particle with perfect accuracy. The more precisely one was measured, the less precisely the other could be known. It wasn't a flaw in instruments or human error. It was the nature of reality itself. The universe, at its deepest level, was built not on determinism but on probabilities. This idea shattered centuries of belief. For generations, scientists had imagined that if we could know every position and velocity of every particle in the universe, we could predict everything: the motion of the stars, the beating of the heart, the fate of the cosmos. But Heisenberg's discovery turned that dream to dust. The universe, it seemed, did not allow absolute knowledge. There was a boundary. a natural limit to what could be known. Beyond that limit lay a fog, not of ignorance, but of fundamental uncertainty. Heisenberg's principle was more than an equation, it was a new philosophy of existence. It spoke of a universe that was alive, dynamic, and mysterious, a universe that did not reveal all its secrets at once. Every measurement, every act of observation, was not a glimpse into fixed truth, but a negotiation with possibility. To look at an electron was to disturb it, to alter its course, to make its future uncertain. The observer and the observed were no longer separate. They were entangled in the dance of knowledge itself. As Heisenberg refined his theory, the world around him began to stir. Quantum mechanics was no longer a collection of strange experiments, it was becoming a language, a way to describe the chaos beneath reality. Heisenberg's uncertainty principle became its grammar, the rule that defined what could and could not be known. His colleagues, men like Niels Bohr, Max Born, and Erwin Schrödinger, began to see that this was not madness but truth. Nature was not a clock, wound and predictable, it was a cloud of possibilities, collapsing into reality only when touched by observation. In Copenhagen, Bohr and Heisenberg spent long nights debating what this truly meant. Was reality only real when measured? Did particles exist before we looked at them? These questions were no longer philosophical riddles. They were scientific frontiers. Heisenberg's uncertainty had opened a door that no one could close. Every step through it brought new revelations and new doubts. The implications were staggering. In the microscopic world, particles did not have fixed paths like planets around a sun. Instead, they existed as waves of potential, mathematical probabilities of where they might be found. When observed, they collapsed into a definite state. This meant that at the deepest level, reality was not composed of solid things, but of possibilities. The act of observation itself brought those possibilities into being. Heisenberg's principle was more than a mathematical restriction. It was a statement about the nature of truth. It said that the universe does not exist as a completed picture waiting to be discovered. It is being painted, moment by moment, through interaction and observation. It was a radical redefinition of knowledge, and it changed not only physics, but the very philosophy of science. Many could not accept it. Einstein, the elder statesman of physics, recoiled at the thought. God does not play dice with the universe, he declared. To him, uncertainty meant chaos, and chaos was unworthy of a rational cosmos. But Heisenberg, young and unshaken, replied with quiet conviction the dice were real, and they were rolling in ways that even gods might not predict. The universe, he believed, was not ruled by chance but by probabilities woven into the very fabric of being. As word of Heisenberg's discovery spread, it sent ripples through every branch of science. The uncertainty principle became a symbol of humility, a reminder that knowledge, no matter how vast, would always face limits. In the laboratories of the world, this new principle guided experiments that would eventually shape technologies of the future. The transistor, the laser, and the quantum computer. All these would trace their lineage to Heisenberg's night of revelation on Helgoland. But beyond the equations and inventions, the uncertainty principle touched something deeper, something almost spiritual. It told humanity that certainty was an illusion, that control was temporary, and that the universe thrived on unpredictability. In a strange and poetic way, Heisenberg had captured the pulse of nature, not static, but beating with randomness and rhythm. In the microscopic world, the uncertainty principle became the law of existence. Electrons no longer orbited like tiny planets, they formed clouds, regions of probability where they might be found. Atoms were no longer miniature solar systems, they were symphonies of possibility. Even light, the most fundamental of forces, could no longer be described as simply a wave or a particle. It was both, depending on how you looked at it. Through Heisenberg's eyes, the world transformed. Every atom, every photon, every flicker of energy became a question, a probability waiting for interaction. Reality was not fixed. It was fluid, relational, dependent on how one asked the question. To measure was to participate. To observe was to alter. The universe was not indifferent, it was interactive. In this new vision, the line between observer and nature blurred. The scientist was no longer a detached spectator, but a participant in creation. Each experiment was an act of dialogue with the cosmos, each observation a whisper exchanged between mind and matter. Heisenberg's uncertainty became a kind of cosmic poetry, a language in which existence itself spoke. Heisenberg once wrote that the path to understanding nature is like walking through a dark forest with a lantern. The light shows only what is near, while the vastness beyond remains hidden. Yet as we move forward, new things are illuminated, and the darkness recedes, though it never disappears entirely. That, he said, is the meaning of uncertainty, the endless unfolding of knowledge, forever limited, forever expanding. The birth of the uncertainty principle was, in truth, the birth of a new worldview. It marked the end of a mechanical universe and the beginning of a probabilistic one. It taught humanity that reality was not built from certainties, but from chances, and that understanding meant embracing the limits of understanding. And yet, there was beauty in that limit, for within uncertainty lay the source of creation itself. Without unpredictability, there could be no freedom, no life, no change. Heisenberg's discovery was not a boundary, it was a doorway. It led physics into new realms, from the quantum field to the fabric of space-time. And it continues to guide scientists today as they search for a unified theory of the cosmos. In that lonely night on Helgoland, when the sea raged and the world seemed unknowable, Heisenberg had glimpsed something eternal. He had seen that the smallest particles, flickering in and out of existence, carried within them the same mystery that stirs in stars, in consciousness, in the unfolding of the universe itself. His uncertainty principle was not just about physics. It was about the nature of reality, the pulse of creation, and the poetry of the unknown. The world that emerged from Heisenberg's discovery was a world unlike any that science had ever imagined, a world in which certainty was no longer the foundation of truth, but its most fragile illusion. What had once been considered unshakable, the deterministic universe of Newton and Laplace, now dissolved into shimmering waves of probability, and from this quantum sea of uncertainty, a new kind of reality was born. As Heisenberg's ideas spread through the scientific world, they found both admirers and adversaries. Many older physicists could not accept that nature itself could be uncertain. To them, uncertainty was an admission of defeat, a sign that human knowledge had reached its limit. But for Heisenberg and his contemporaries, it was the opposite. It was liberation. For the first time, science had found a way to describe the indescribable, not by clinging to certainties, but by embracing the delicate balance between what can be known and what must remain hidden. At the heart of this revolution lay Heisenberg's mathematical insight, Trex Tatar P1 by 2, the equation that defined the relationship between position x and momentum Lipeve. It was a simple expression, but its meaning was profound. The more precisely one knew where a particle was, the less precisely one could know where it was going. This was not a limitation of instruments or human error. It was a property of the universe itself, woven into the very fabric of quantum reality. In the microscopic world, this uncertainty became the rule of existence. Electrons no longer moved like marbles rolling along a track, they danced in patterns of probability. Around an atomic nucleus, they formed shimmering clouds, zones of possibility where the electron might be found, but never with certainty. Each particle was not a fixed point, but a wave of potential. The classical idea of a well-defined path or trajectory was gone. Nature had replaced it with the strange logic of the quantum. This realization forced scientists to rethink everything they thought they knew about causality. In Newton's world, every event had a cause, and every cause had an effect. The future could be predicted if one knew the present. But in Heisenberg's world, that perfect chain of causation broke apart. One could no longer predict a single future, only a range of possible outcomes, each with its own probability. The universe was not a script already written. it was an improvisation unfolding in real time. The philosophical consequences were immense. The uncertainty principle suggested that the observer and the observed could not be separated. When a scientist measured a particle, they were not merely discovering its properties. They were participating in the creation of those properties. The act of observation collapsed the particle's wave of possibilities into a definite state. Before the measurement, it was not that the particle's position or momentum was unknown. It was that they did not yet exist in any definite form. Observation brought reality into being. This was a staggering notion. It implied that reality was not entirely objective, not fully independent of consciousness or measurement. The universe, at least at the quantum level, was relational, defined by interactions rather than by intrinsic properties. The world was not a collection of things but a network of events. For many, this blurred the line between science and philosophy. Was the act of measurement a kind of creation? Was the observer a participant in the making of the universe? These questions rippled through the minds of the greatest thinkers of the time. Niels Bohr, Heisenberg's mentor and collaborator, proposed that this was the essence of quantum mechanics: complementarity. The idea that wave and particle, certainty and uncertainty, observer and observed, were not opposites but partners in a single, indivisible reality. In this light, the uncertainty principle became not a statement of ignorance, but a declaration of unity. It told us that to observe nature is to become part of it, that the fabric of reality is woven through interaction. Heisenberg's discovery was not just a milestone in physics, it was a revelation about existence itself. The microscopic world, once imagined as a miniature version of the macroscopic one, turned out to be far stranger. Time and space, cause and effect, even identity, lost their familiar meanings. A particle could exist in multiple states at once, a phenomenon known as superposition. It could pass through two slits simultaneously and interfere with itself. It could entangle with another particle so completely that the state of one instantly influenced the other, even across vast distances. All of these phenomena arose naturally from the uncertainty that Heisenberg had uncovered. To many scientists, this was both exhilarating and terrifying. Quantum mechanics worked. Its predictions matched experiments with breathtaking precision, yet its implications defied common sense. Heisenberg himself often admitted that even he did not fully understand quantum mechanics in the way one understands a clock or an engine. It was not a theory that revealed how nature should behave. It was a theory that described how nature does behave, however strange that may seem. Over time, the uncertainty principle began to reveal its hidden beauty. It explained why electrons do not collapse into the nucleus. Their uncertain momentum keeps them in motion. It set the boundaries for what can be known, ensuring that energy and time, position and momentum, exist in a delicate balance. Without uncertainty, atoms themselves would be impossible. The stability of matter, the light from the stars, the very chemistry of life, all depend on this principle. In this sense, Heisenberg's discovery was not a curse of ignorance but a gift of creation. The same uncertainty that limits human knowledge also allows the universe to exist. It gives rise to motion, to fluctuation, to change, to life itself. The world is dynamic precisely because it is uncertain. Beyond the laboratory, Heisenberg's principle resonated deeply with the spirit of the age. The early 20th century was an era of transformation in art, politics, and philosophy. Certainty was collapsing everywhere. Old empires fell, new ideologies rose, and human identity itself seemed fluid and uncertain. In painting, cubism fractured space and perspective. In music, atonality shattered harmony. In literature, stream of consciousness replaced linear narrative. Heisenberg's uncertainty fit perfectly into this cultural revolution. It was as though nature itself had joined the chorus, declaring that reality, too, was fluid, dynamic, and indeterminate. As the years passed, the uncertainty principle became one of the most tested and validated ideas in all of science. Every experiment confirmed it, every attempt to disprove it only deepened its truth. In the quantum realm, Uncertainty was not a sign of weakness. It was the signature of existence. Yet Heisenberg himself remained humble before its mystery. He often said that the deeper he delved into quantum theory, the more he felt a sense of awe. The first gulp from the glass of natural sciences, he once remarked, will turn you into an atheist, but at the bottom of the glass, God is waiting for you. What he meant was not religion but reverence, an acknowledgement that knowledge, no matter how vast, always opens into greater mystery. Today, nearly a century after its discovery, the uncertainty principle continues to shape the frontier of science. It governs the behavior of quantum computers, defines the limits of measurement in particle accelerators, and guides the exploration of black holes and the early universe. Even in cosmology, the echo of Heisenberg's insight can be heard. The tiny quantum fluctuations that once filled the infant universe became the seeds of galaxies. Uncertainty, quite literally, gave birth to the cosmos we see today. In the end, the meaning of the uncertainty principle goes far beyond physics. It is a mirror held up to the human condition. It tells us that to seek knowledge is noble, but to accept limits is wise. It teaches that the universe is not something to be conquered, but something to be understood, not through dominance, but through participation. When Heisenberg sat on that lonely island in 1927, he could not have imagined how far his revelation would reach. What began as a struggle with equations became a philosophy for all of science, a reminder that even in the smallest scales of nature, mystery endures. The uncertainty principle did not close the book of physics, it opened an infinite new chapter. The microscopic world that Heisenberg unveiled is not a place of chaos, but of harmony. A harmony that arises from balance, from the dance between knowledge and mystery, order and chance. In its rhythm, we find not confusion but connection. The universe is not broken by uncertainty, it is made alive by it. And so, as modern physicists probe deeper into quantum fields and spacetime foam, they still carry Heisenberg's torch, the understanding that uncertainty is not an obstacle to truth, but its most profound expression. The more we learn, the more we realize that the fabric of existence is woven with both light and shadow, that what cannot be known is as vital as what can. Heisenberg's principle, born from sleepless nights and endless curiosity, stands as a testament to the human spirit. The courage to ask, to doubt, to wonder. It reminds us that the universe is not a riddle to be solved, but a mystery to be lived. And somewhere in that mystery, in the quiet trembling of the quantum world, the story of everything continues to unfold. Before Heisenberg, measurement in science was considered a neutral act, an unintrusive glance at reality, a way to uncover facts that existed independently of the observer. The tools of physics were extensions of human perception, instruments designed to reveal nature's secrets without disturbing them. A clock told the time, a telescope charted the stars, a thermometer measured the heat, all assumed to capture truth objectively. Newtonian mechanics had reinforced this idea. The universe was a machine whose every gear and motion could be recorded without consequence. Measurement was passive, a window to a reality that existed exactly as it appeared. Heisenberg's insight shattered that comforting illusion. The uncertainty principle demonstrated that the act of measurement itself was not neutral. To observe a particle's position or momentum was to influence it in a fundamental way. It was not merely a limitation of instruments, it was a law of nature. At the quantum level, nature could not be separated from its observation. The observer was no longer an outsider looking in, but an integral participant in the unfolding of reality. This revelation forced a profound reevaluation of what it meant to measure anything. In the classical world, measuring a planet's position or speed did not affect its motion. In the quantum world, however, the tiniest interaction, a photon bouncing off an electron, the magnetic field of an instrument influencing a particle, changed the outcome. Heisenberg's principle formalized this effect mathematically. The more precisely one tries to determine a particle's position, the less precisely one can know its momentum, and vice versa. Measurement was now a dialogue, not a simple observation. The consequences of this shift were both practical and philosophical. Scientists could no longer claim that they were passively recording nature. Every act of measurement had a footprint, every observation a consequence. Experiments in quantum mechanics became exercises not only in precision, but in understanding the limits imposed by the universe itself. Electrons no longer had definite trajectories that could be mapped. Their behavior could only be predicted probabilistically. Measurement did not reveal a pre-existing property but helped define it. Reality was participatory, not merely observed. This participatory nature of observation also redefined the role of the scientist. No longer could a physicist claim complete detachment from the system under study. Every experiment, every calculation, every measurement had to account for the fact that the act of looking altered the phenomenon. This was not an inconvenience but a profound insight into the fabric of reality. Observation was an intervention, a creative act that brought certain aspects of the quantum world into focus while leaving others forever undefined. Heisenberg's insight also transformed the way experiments were designed. Quantum experiments were no longer just about building more accurate instruments. They became exercises in understanding limits. Physicists learned to embrace statistical outcomes, to work with probabilities rather than deterministic predictions. The nature of error itself was recast. Uncertainty was not just noise in measurement, but a fundamental property of nature. The precision of instruments could be improved, but the uncertainty principle set a boundary beyond which nature itself would not yield. Philosophically, this reshaping of measurement echoed far beyond physics. It questioned the very notion of objectivity and the idea that the universe exists fully independent of our awareness. Reality was not merely out there, waiting to be discovered. It emerged through interaction. This subtle yet radical change in perspective influenced other fields as well, from philosophy to cognitive science. It introduced a humility into human inquiry, a recognition that some aspects of nature are intrinsically inaccessible, and that understanding often involves embracing limits as much as uncovering facts. The redefinition of observation also gave rise to the famous debates between Heisenberg and Einstein. Einstein could not accept that nature itself could be probabilistic. He believed that measurement revealed ignorance, not fundamental indeterminacy. For Heisenberg, however, the limits imposed by observation were inherent, not accidental. The act of measurement did not merely expose a hidden variable, it participated in shaping reality. This tension between the deterministic ideal and the probabilistic truth became one of the defining dialogues of modern physics. In laboratories, this understanding changed the way scientists approach quantum systems. Rather than attempting to pinpoint exact positions and momenta, physicists mapped probability distributions, calculated likelihoods, and worked with wave functions. Experiments were interpreted in terms of outcomes that could occur rather than certainties that must occur. Observing a particle was no longer a matter of reading its location. It was a negotiation with possibility. The act of measurement became inseparable from the reality it sought to reveal. Even at a conceptual level, this shift altered humanity's view of reality. It taught that knowledge is relational, that to know something fully, one must acknowledge the limits of knowing. The universe was no longer a detached backdrop to human observation. It was an interactive canvas, where the observer and the observed were entwined in an inseparable dance. This understanding reshaped the philosophy of science, moving it from the pursuit of absolute truth to the careful navigation of possibilities and interactions. Heisenberg's redefinition of measurement also provided clarity to other mysteries of the quantum world. Phenomena such as quantum superposition and entanglement, once baffling, made sense when seen through the lens of participatory observation. A particle's state was not fixed until measured. Reality was not singular until observed. Entangled particles influenced one another instantaneously because their properties were defined relationally, not independently. The role of measurement in this context was not trivial. it was constitutive. In practical terms, this reimagining of observation paved the way for countless technological advances. From quantum computing to high-precision spectroscopy, the recognition that measurement alters reality enabled scientists to design experiments that exploit, rather than fight against, the probabilistic nature of the microscopic world. Heisenberg's principle turned limitation into opportunity, guiding researchers to work within the fundamental constraints of nature rather than attempting the impossible. Ultimately, the legacy of Heisenberg's redefinition of measurement is both scientific and philosophical. It reminds humanity that observation is never neutral, that every act of inquiry changes the system being studied. It teaches that certainty is a relative concept and that reality itself is participatory. In this way, Heisenberg did not merely provide a new rule for physics, he gave the world a new lens through which to see existence. One in which knowledge, uncertainty, and observation are bound together inextricably. Through this lens, the microscopic world becomes a dynamic, interactive realm where limits are not failures but defining characteristics. Particles are not static, properties emerge through engagement. Measurements are not passive, they are creative acts. The universe, in its most intimate and fundamental form, is alive with relational complexity, and our understanding of it is forever entwined with how we interact with it. Heisenberg's work teaches a lesson that extends far beyond the laboratory. It is a meditation on the nature of reality itself, an invitation to embrace uncertainty, and a reminder that the act of observation is inseparable from the existence it seeks to reveal. Measurement is not merely a tool, it is a bridge between possibility and actuality, between potential and the world we experience. In redefining the very act of seeing, Heisenberg reshaped the human understanding of knowledge, forever altering the way we perceive the universe. The discoveries of Werner Heisenberg did not merely change the way physicists viewed the microscopic world, they opened a gateway to a future in which the boundaries between imagination, theory, and application began to blur. At first, the uncertainty principle and the foundations of quantum mechanics seemed almost like abstract curiosities, strange rules governing invisible particles that could not be seen with the naked eye. Yet as the decades unfolded, it became increasingly clear that the microscopic mysteries Heisenberg revealed were the very seeds of a technological revolution that would transform human life. The implications for physics were immediate and profound. Classical physics, with its predictable orbits and absolute laws, was no longer sufficient to explain the behavior of matter at the smallest scales. Electrons, photons, and atomic nuclei demanded a new framework, one that embraced probability, waves, and discrete energy states. Heisenberg's work provided that framework, giving scientists a precise language to describe phenomena that had previously defied understanding. Quantum mechanics became the map by which the unseen world could be navigated, turning uncertainty from a hindrance into a tool of exploration. This new understanding allowed physicists to predict behaviors that were once considered impossible. The stability of atoms, for example, could now be explained through the interplay of uncertainty and quantized energy levels. Electrons, though uncertain in position, could exist in stable orbits without collapsing into the nucleus. Photons could behave simultaneously as particles and waves, giving rise to the duality that underpins much of modern physics. Heisenberg's insights, therefore, were not just theoretical, they provided the foundation upon which all subsequent quantum theory would be built. But the implications went far beyond theory. As scientists began to manipulate quantum effects, the principles Heisenberg had uncovered began to take on practical significance. The development of semiconductors, the foundation of modern electronics, depended on understanding the behavior of electrons in materials, behavior governed by quantum mechanics. The laser, another transformative technology, relies on the precise control of energy states and photon emissions, phenomena that could only be explained through the language of uncertainty and quantum theory. What once seemed abstract became tangible, and what was theoretical became instrumental in shaping the modern world. Even computing, a field that would revolutionize human society, owes much to the quantum understanding Heisenberg helped establish. Conventional computers operate on binary states, but quantum computers exploit the superposition and entanglement of particles, allowing multiple computations to occur simultaneously. These machines promise to solve problems that classical computers could never handle, from modeling complex molecular interactions to breaking encryption codes. The uncertainty principle, once considered a limitation, is now a guiding principle in designing these cutting-edge devices, highlighting how fundamental insights can evolve into transformative tools. Beyond technology, Heisenberg's work reshaped the trajectory of scientific inquiry itself. Quantum mechanics introduced a new way of thinking, where probability replaced determinism and observation was intertwined with existence. This shift prompted a reconsideration of experimental design, forcing scientists to account for the influence of measurement on the system being studied. Experiments were no longer simply about recording outcomes, they became intricate exercises in controlling interactions and interpreting probabilities. The philosophy of experimentation was forever altered, and with it, the very approach to understanding nature. The ripple effects extended even further. Nuclear physics, which would underpin both energy generation and medical imaging, was made possible through quantum mechanics. Understanding atomic nuclei and their interactions required grappling with the same principles of uncertainty that Heisenberg articulated. Nuclear power plants, MRI machines, and radiation therapy for cancer patients, all are products of insights that trace back to the conceptual revolution initiated by the uncertainty principle. The microscopic, once invisible and irrelevant to daily life, had become central to human existence. Heisenberg's work also laid the conceptual groundwork for exploring the universe at its largest scales. Cosmology and particle physics increasingly rely on quantum principles to understand the origins of matter, the behavior of subatomic particles in high-energy collisions, and the processes occurring within black holes. The principles of uncertainty are not confined to the laboratory, they govern the evolution of stars, the formation of galaxies, and perhaps even the fundamental structure of space and time. By revealing the limits of what can be known, Heisenberg challenged physicists to think creatively about the cosmos, inspiring a generation to explore questions that bridge the infinitely small and the infinitely large. Philosophically, the impact of Heisenberg's work is equally profound. It reshaped humanity's understanding of knowledge and reality, emphasizing limits and probabilities rather than absolutes. The recognition that observation influences outcomes has parallels in fields as diverse as psychology, information theory, and even economics. The principle teaches humility in the face of complexity. No system can be entirely disentangled from the act of observing it, and no prediction can be entirely free of uncertainty. It is a lesson that resonates not only in science, but in the way humans approach the world at large. Ultimately, the legacy of Heisenberg's discoveries is one of transformation. He revealed that the universe operates on principles far removed from everyday intuition, and in doing so, he provided the keys to harness those principles. The uncertainty principle, which at first seemed to limit knowledge, became a source of power, guiding technological innovation, informing scientific methodology, and shaping the philosophy of the 20th and 21st centuries. It is a testament to the idea that understanding the rules of nature, even at the smallest scales, opens possibilities far beyond what we can initially imagine. In every modern device, from the smartphones in our hands to the quantum sensors that map the unseen, the echoes of Heisenberg's work are present. The microscopic world he revealed underpins the macroscopic achievements of humanity. Without acknowledging uncertainty, we could never have developed the precision technologies that define modern life, nor could we explore the universe with the confidence that comes from understanding, even probabilistically, the behaviors of its most fundamental constituents. In this way, Heisenberg's contributions serve as both a caution and an inspiration. They caution us that knowledge has limits and that reality often defies intuition. Yet they also inspire, showing that within those limits lie endless possibilities for discovery, innovation, and understanding. The microscopic world is not simply strange, it is fertile, full of principles that guide the creation of technologies and ideas capable of reshaping the world. Through the lens of Heisenberg's insights, the future of physics became a landscape of potential. It showed that the mysteries of the quantum world are not obstacles to progress but engines of it, driving the development of tools, techniques, and technologies that continue to expand the horizons of human capability. The implications of his work extend beyond equations and laboratories, touching every aspect of modern life, every frontier of scientific inquiry, and every philosophical reflection on the nature of reality itself. When Werner Heisenberg unveiled the uncertainty principle, he did more than introduce a mathematical limit to measurement. He opened a philosophical Pandora's box that would reverberate across the world of science. The quantum revolution, which he helped to ignite, challenged not only classical physics, but the very assumptions about reality that humanity had held for centuries. What began as a technical insight into the behavior of subatomic particles quickly evolved into profound questions. What is real? Can we truly know nature? Does the observer shape the universe? Heisenberg had placed the microscope on not just atoms, but on the foundations of human thought. For centuries, the Newtonian worldview had been the bedrock of scientific philosophy. Reality was objective, measurable, and deterministic. Every effect had a cause, every motion could be traced, and the universe operated like a grand clockwork mechanism. To know was to observe without influence, to understand was to capture truth in its entirety. Heisenberg's principle tore through that comforting narrative. At the quantum level, knowledge was inherently probabilistic. Observation altered what was observed, and certainty was replaced by ranges of possibility. The universe, it seemed, was far less a predictable machine than a dynamic interplay of forces and probabilities. These ideas sparked intense debate among the greatest minds of the era. Albert Einstein, a titan of theoretical physics, was deeply unsettled by Heisenberg's conclusions. For Einstein, uncertainty implied imperfection in nature, a flaw in the underlying design of reality. God does not play dice with the universe, he famously declared, insisting that hidden variables must exist, factors beyond the reach of measurement, that would restore determinism to physics. To Einstein, quantum mechanics, while useful, was incomplete. It described phenomena but did not reveal ultimate truth. Heisenberg, along with Niels Bohr and other pioneers of quantum mechanics, offered a strikingly different view. They argued that nature itself imposes limits on what can be known and that these limits are not deficiencies, but fundamental characteristics of reality. The universe at its smallest scales is inherently probabilistic. Particles do not have fixed positions or velocities independent of measurement. The debates that unfolded between Heisenberg and Einstein were not merely technical arguments. They were confrontations between two philosophical visions of reality. Determinism clashed with probability, absolutes with relationality, certainty with inherent ambiguity. The philosophical impact of this clash extended far beyond physics. If Heisenberg was right, then knowledge is not a neutral mirror reflecting reality, but an active process that interacts with what is being known. Observation shapes outcomes. Measurement is participatory. This idea reverberated through the philosophy of science, forcing scholars to reconsider the nature of objectivity. Reality was no longer a fixed stage on which events played out independently of human observation. Instead, it became a co-created tapestry, where the act of engagement influenced what could be said about existence. These debates also reshaped the way scientists conceived of experiments. In the classical model, experiments could, in principle, be performed without affecting the system under study. In the quantum world, such detachment was impossible. Every observation carried consequences. The design and interpretation of experiments required an awareness that the observer and the observed were interconnected. Heisenberg's principle became both a technical guide and a philosophical statement. Understanding nature demands humility, rigor, and acknowledgement of limits. The broader intellectual community took notice. Philosophers, mathematicians, and even artists drew inspiration from the radical new conception of reality. The uncertainty principle became a metaphor for the complexity of knowledge, the limits of perception, and the fluidity of existence. It suggested that the universe is not a closed book of facts, but an ongoing narrative shaped by interaction, observation, and choice. In this sense, Heisenberg's work transcended physics, touching every domain where inquiry and observation intersect. One of the most striking consequences of these philosophical debates was the concept of complementarity, championed by Niels Bohr. Bohr argued that seemingly contradictory aspects of quantum entities, wave and particle, certainty and uncertainty, are both necessary for a complete understanding. Heisenberg's uncertainty principle provided the mathematical foundation for this view, demonstrating that opposing properties cannot be simultaneously known with precision. This complementarity reshaped the way scientists thought about dualities, not just in physics, but in the interpretation of reality itself. The debates also forced physicists to confront the limits of human intuition. The microscopic world operates according to rules that defy common sense. Electrons exist as clouds of probability rather than particles with defined paths. A photon can behave as a particle in one experiment and a wave in another, depending on how it is observed. These behaviors cannot be fully reconciled with everyday experience, yet they are objectively measurable and reproducible. Heisenberg's work demanded a shift in thinking. The universe is stranger than imagination, yet accessible through the language of mathematics and probability. Cultural and philosophical interpretations followed naturally. Writers and thinkers saw parallels between quantum uncertainty and human experience. Just as particles occupy multiple states until measured, so too can human lives unfold in a web of potentialities influenced by choices and context. Observation, context, and interaction shape outcomes in both physics and life. In this sense, Heisenberg's ideas resonated far beyond laboratories, influencing how humanity conceptualizes knowledge, agency, and reality itself. Even within physics, the debates sparked by Heisenberg's work continue to this day. Questions about hidden variables, the nature of wave function collapse, and the interpretation of quantum mechanics, such as the Copenhagen interpretation versus many worlds theory, all trace their roots to the philosophical challenges raised by the uncertainty principle. These discussions remind us that science is not only a technical endeavor, but a dialogue with reality, constantly testing assumptions, revising understanding, and balancing evidence with philosophical reflection. In essence, Heisenberg's influence on quantum philosophy was as profound as his technical contributions. By revealing that measurement and observation are active participants in the creation of reality, he forced a reevaluation of what it means to know, to measure, and to exist. The debates he sparked illuminated the tension between determinism and probability, certainty and ambiguity, observation and reality, tensions that continue to inspire inquiry, debate, and discovery. His work demonstrated that the pursuit of knowledge is not a linear path from ignorance to truth, but a dynamic interaction with the universe. Understanding requires engagement, and engagement imposes limits. The universe is not a passive object, but a partner in the act of discovery. In redefining the nature of observation, Heisenberg forever altered the relationship between human beings and the cosmos, embedding philosophy into the practice of physics. In the final analysis, the legacy of Heisenberg's influence on quantum philosophy is a reminder of both humility and possibility. It teaches that even the most carefully measured reality retains a layer of mystery, that knowledge is not omnipotent, and that every act of observation carries consequences. By challenging the classical assumptions of determinism and absolute objectivity, Heisenberg reshaped the very framework through which humanity understands nature, opening doors to new interpretations, new technologies, and a deeper appreciation of the universe's profound complexity. The debates sparked by his work were not just academic, they were existential. They forced scientists, philosophers, and thinkers to confront the limits of perception, the fluidity of reality, and the participatory nature of knowledge itself. Heisenberg showed that science is as much a conversation with the universe as it is a measurement of it, a dialogue in which observation and reality are inseparably intertwined, and in which the act of knowing is itself a transformative experience. The impact of Werner Heisenberg's work extends far beyond the realm of physics. It reaches into the very way humanity perceives reality, knowledge, and the role of observation in shaping the world. His discoveries, most notably the uncertainty principle, did not merely redefine atomic theory. They altered the intellectual landscape of the 20th century and set the stage for the scientific revolutions that continue to unfold today. The legacy of his work is not measured solely in equations or experiments, but in a fundamental transformation of human thought. Heisenberg demonstrated that the universe, at its most elemental level, does not conform to deterministic laws as once imagined. Classical physics had taught that, given complete knowledge of all initial conditions, the future of the universe could be predicted with absolute certainty. This was the Newtonian dream, a clockwork cosmos governed by immutable laws. Heisenberg shattered that notion, showing that uncertainty is inherent in the fabric of reality. Position and momentum, energy and time, cannot simultaneously be measured with arbitrary precision. This insight introduced a limit to knowledge, a fundamental horizon beyond which the universe cannot be probed. Yet within that limitation lies the beauty and the power of nature. The legacy of this revelation is twofold: theoretical and practical. On a theoretical level, Heisenberg's work provided the foundation for modern quantum mechanics. It offered a framework for understanding the behavior of particles, atoms, and molecules, a framework that would become indispensable for nearly all of modern physics. Without his insights, the development of quantum field theory, particle physics, and the Standard Model would have been impossible. Every contemporary physicist stands on the shoulders of the intellectual skyscraper that Heisenberg helped to construct, a structure built on the acceptance that probability, rather than certainty, governs the quantum world. Practically, Heisenberg's legacy is visible in technologies that shape everyday life. The principles of quantum mechanics underpin semiconductors, which power computers and smartphones. Lasers, another product of quantum understanding, are found in everything from barcode scanners to medical devices. Magnetic resonance imaging, RIFE, a critical tool in modern medicine, relies on quantum principles to visualize the interior of the human body without invasive procedures. The uncertainty principle, once an abstract mathematical concept, became a guiding principle in designing tools that manipulate matter and energy at the smallest scales. Beyond technology, Heisenberg's work continues to influence philosophical thought and the way humanity approaches knowledge. By revealing that the act of measurement influences outcomes, he challenged the notion of objective observation as an unchanging window into reality. Reality is participatory, relational, and contingent on interaction. Observation is no longer a neutral act, it is a creative one. In science, this reshaped experimental design, data interpretation, and the understanding of causality. In philosophy, it suggested that knowledge is inseparable from experience and engagement, that understanding is limited, and that uncertainty is not failure but a natural condition of existence. Heisenberg's ideas also resonate in the ongoing exploration of the cosmos. Quantum mechanics, built upon the uncertainty principle, informs our understanding of particle interactions in the early universe, the behavior of black holes, and the properties of dark matter and dark energy. The tiniest fluctuations in quantum fields, the very uncertainties Heisenberg described, seeded the structure of galaxies and cosmic formations. In this sense, uncertainty is not merely a limitation, it is a driver of creation and complexity in the universe itself. The legacy of his work bridges the infinitely small with the infinitely large. connecting atomic behavior to the evolution of the cosmos. The debates he initiated continue to inspire scientific inquiry. Philosophical and experimental questions about hidden variables, wave function collapse, and the interpretation of quantum mechanics remain central to contemporary physics. The uncertainty principle forces scientists to continually reevaluate assumptions and push the boundaries of understanding. The principle itself has become a tool of innovation, guiding research into quantum computing, quantum cryptography, and quantum communication, fields that promise to redefine computing power, security, and the transmission of information. Culturally, Heisenberg's discoveries altered how people perceive reality and possibility. His work suggests that certainty is an illusion and that unpredictability is intrinsic to the universe. In art, literature, and thought, uncertainty has become a metaphor for the richness and complexity of existence. Just as electrons inhabit clouds of probability, human lives are shaped by choices, interactions, and contingencies. The principle of uncertainty resonates with broader human experience, emphasizing adaptability, humility, and openness to the unknown. Heisenberg's legacy is also a testament to intellectual courage. In a world accustomed to definitive answers, he dared to embrace ambiguity and articulate a reality governed by probabilities. He challenged the comfortable certainties of classical physics and invited humanity to see the universe in a new light, a light that illuminates possibility, flexibility, and interconnectedness. By redefining what can be known, he expanded the horizons of imagination and inquiry, demonstrating that the limits of knowledge are not constraints but gateways to deeper understanding. Even today, nearly a century after Heisenberg's revelations, his work continues to shape scientific and philosophical discourse. Quantum mechanics, with all its counterintuitive phenomena, remains one of the most successful and tested theories in science. Yet its interpretation, its philosophical implications, and its technological potential continue to provoke debate, discovery, and inspiration. The uncertainty principle reminds us that science is not merely about certainties, but about exploring the interplay between knowledge and possibility. Ultimately, the lasting legacy of Heisenberg's work lies in its dual power to challenge and to enable. It challenges humanity to accept the limits of observation and the inherent unpredictability of the universe. It enables us to harness these principles to create technologies, conduct research, and develop a richer understanding of the cosmos. His work transformed science from a search for absolute certainty into a dynamic engagement with nature, where knowledge is provisional, observation is participatory, and discovery is continuous. Heisenberg's contribution is not just a chapter in the history of physics, it is a lens through which the modern world views itself. It teaches that even at the smallest scales, the universe is alive with possibility, and that uncertainty is not absence but a foundation for creation. In embracing the unknown, humanity gains insight. In accepting limits, it gains freedom to innovate. And in recognizing the interplay between observation and reality, it gains a deeper understanding of existence itself. From the quantum laboratories of today to the philosophical reflections that shape human thought, the echo of Heisenberg's discoveries continues to resonate. His work reminds us that the universe is not a static, predetermined machine but a living, dynamic system in which the act of knowing is inseparable from the act of being. The uncertainty principle, once a radical insight, has become a cornerstone of modern science, a guiding principle for inquiry, and a profound meditation on the nature of reality. In every sense, Heisenberg's legacy endures, in the science that builds our technology, in the philosophy that shapes our understanding, and in the ongoing human quest to explore, to question, and to engage with the universe. His revelations transformed the microscopic world, and in doing so, they transformed the human perspective itself, leaving an indelible mark on the story of knowledge, discovery, and the infinite possibilities of reality.